Hi everyone! Welcome to part 1 of chapter 5. Today begins our chapter on the mole. The mole is a major topic in chemistry, and it allows us to weigh out amounts of substances and do a lot of cool calculations during our reactions. So before I get too much into it, let's just go ahead and jump to this first slide. So atoms are really small, like really small, right? If I asked you, hey, can you count out 4 atoms of carbon for me? You'd be like, no, I can't count out 4 atoms of carbon. They're just too small, right? Even a teensy amount of matter that we might be working with in our lab would contain so many atoms. So it's not reasonable for us to sit there and go 1 atom of carbon, 2 atoms of carbon, right? It doesn't make any sense. So instead, we use the mole. It's a really convenient item for atoms that are measured out on the macro scale, which is what we're doing in lab. So you can kind of think about it this way. If you were going to go to Save Mart or Food Max or wherever you're going, right, and you're going to buy some fruit, you don't go, okay, I'm going to go over to the grapes and I'm going to buy 20 grapes, right? And I'm going to count out my little grapes and then I'm going to eat, right? You don't do that. Instead, you grab a bag of grapes and they weigh it and they tell you how much it costs, right? That's essentially what we're doing with our atoms. We don't count out individual atoms. We take a mass and that will tell us how many atoms are in that amount of mass. It's the same thing you're doing with the grapes. Like if we know each grape weighs a certain amount, we can use this mass or this weight that the checker is weighing out, and that will tell us how many grapes you're buying, rather than sitting there and counting all of them. We do the same thing with atoms. Kind of cool. So an example using oranges. Let's say we have an orange and we know this mass of this orange is 186 grams. Well, what then is the mass of 75 oranges? Okay, so this is a conversion factor. 1 orange equals 186 grams. So if I wanted to use this to figure out the mass of 75 oranges, a lot of you are maybe doing this in your head, but if you're not, right, we would start with our 75 oranges at the beginning of our train track. Remember, from our last talk, we never start train tracks with conversion factors, right? So if 1 orange equals 186 grams, that's a conversion factor, and we can't start with that. So instead, we start with 75 oranges. So here's our conversion factor. 1 orange equals 186 grams. So remember, oranges have to cancel oranges down to the right. So 1 orange will go on the bottom and 186 grams will go on the top. So we can actually figure out the mass of 75 oranges without having to weigh 75 oranges. Because if we know the mass of 1 orange, then we can know the mass of 75 oranges. Okay, so we do this exact same thing essentially in chemistry. If we know the mass of 1 carbon atom, we can know the mass of thousands of carbon atoms by multiplying their masses just like we've done here. Okay, so we already have words that mean numbers in English. Like if I told you, hey, go to the store and buy a dozen eggs. Well, you know that a dozen is equal to 12 eggs, right? Or you might even know a baker's dozen. If you don't, a baker's dozen is 13. But again, words that mean numbers. Or like a ream of paper is 500 sheets. All teachers know that one. Or you might know that pencils are measured by a gross, which is 144, right? So we have words that mean numbers. It's the same thing in chemistry. This word mole is not a cute little critter. Well, I mean, it is. Moles are cute little critters. But the word mole in chemistry means a number. And it's a huge number. It's 6.022 times 10 to the 23rd. Okay? We will only use this to talk about atoms and talk about molecules because realistically, that's the only thing small enough to use that many. Like if I wrote this out in, regular form, 6.022 times 10 to the 23rd, that would be this. That's that number, okay? So you can see that atoms and molecules are really the only thing small enough to have that many of. but a mole just means that many of something. Okay, this number, instead of always saying 6.022 times 10 to the 23rd, this number is called Avogadro's number. So oftentimes you'll hear me say Avogadro's number. So if I say that, I mean this. But the reason we use this number is so that we can measure out very large amounts of teeny tiny little atoms. Okay, and this mole we use very similar to other units of counting, where we would use it just like we would use a dozen or a gross, right? This word means a number just like those words mean numbers. So moles can be used to describe elements, particles, or compounds. Typically, we will use it to mean atoms or molecules. Those are the two applications of it in this class. So if you have a mole of atoms, that's saying you have 6.022 times 10 to the 23rd atoms. Just like saying if you have a dozen eggs, that means you have 12 eggs. Okay, it's the same thing. 1 mole just means 6.022 times 10 to the 23rd of whatever it is. You could have a mole of puppies, and you would have 6.022 times 10 to the 23rd puppies, right? It's not exclusive to atoms and molecules. They're just really the only things small enough to count with this gigantic number. Okay, but we could use it for atoms, molecules, and then in other classes you may even use it for electrons as well. Okay, so the reason that Avogadro's number, right, that's 6.022 times 10 to the 23rd, the reason that that number is really useful is because it's an equality, so we can use it as a conversion factor. Okay, so remember, when things are equal, they're going to get stacked in our train tracks, so we can use it as 1 mole over 6.022 times 10 to the 23rd, or we can use it as 6.022 times 10 to the 23rd on the top and 1 mole on the bottom. It's just going to depend on how we need our units to cancel, just like we've been doing already. So Avogadro's number is used to convert between moles of a substance and atoms, or moles and molecules. Okay, so like here, this says convert 4 moles of iron to atoms of iron. And this conversion factor you are going to need to know. 1 mole is equal to 6.022 times 10 to the 23rd particles. But don't worry, you're going to use this a lot in this class, and it's one of those things that you'll kind of accidentally memorize if you get enough practice. So let's figure out what we're starting with. This is our actual problem here, so the only number we see is this 4 moles of iron. So that's going to go in the beginning of our train track. It's really important to start building good habits right now. This chapter kind of starts a larger unit on calculations in chemistry. And when we do these train tracks, you're always going to want to put a number, a unit, and a chemical every single time in every single box. Put a number, a unit, and a chemical. So we have 4 moles of iron. You'll notice here that I put MOL. That's not a typo. That's actually the abbreviation for mole. So mole is MOLE, and we abbreviate it MOL. I know that's a little bit silly that all we've done is take off the E, but just be really careful that you don't abbreviate it as just M. Remember, just M is meters or mass, but not moles, so be careful. Okay, so 4 moles of iron. So we'll make our train track here. And now we're trying to convert moles of iron to atoms of iron. The way we get between moles and atoms is Avogadro's number. Okay, you'll notice I wrote the word particles here. Particles means either atoms or molecules. It's just so I don't need to write 2 conversion factors, 1 for each. All right, so following our rules of train tracks, moles of iron needs to cancel moles of iron. So if I have moles of iron here, then that means this 1 mole needs to go on the bottom, and 6.022 times 10 to the 23rd atoms will go on the top. You'll notice for both of these, I have the number, the unit, the chemical. Number, unit, chemical for both of them, so be careful about that. Okay, 1 mole of iron goes on the bottom, and then you'll notice I replaced the word particles with the word atoms to match what we were trying to find. Okay, we make sure moles of iron cancels moles of iron, and then we'll multiply these numbers together and get 2.41 times 10 to the 24th atoms of iron. Okay, what I want you to do right now is actually punch this in your calculator. If you have the TI 32X2S, the one that I recommend for this class, you'll notice that above the x to the minus 1 button, there's a double E. Hopefully you can find that. If you use that double E button, it's going to make your life a lot easier. So what you can do is you can type in 6.022, hit the second function, and then x to the minus 1, and it will put an E right there. And that E means times 10 to the. And then you can just write 23. So it'll look a little bit silly, but it'll look like 6.022 E23. Okay? And if you type it in that way, that's allowing you to do these calculations without having to use parentheses. Okay? The biggest issue I have found in the beginning of this chapter is that people are using their calculator incorrectly. And they're not putting parentheses around that, or they're not putting parentheses around it correctly, or they're doing something else weird, usually related to the exponent. So if you do this with this double E button, then that will kind of alleviate a lot of those problems because now you don't need parentheses. Okay, so I would practice punching this in. 4.00 times 6.022 second function, x to the minus 1, we'll drop that E there, and then 23. You'll notice no times, no 10, no to the, just E23. If you have a Casio, you likely have a times 10 to the x button. If you find that button, it actually works just like the double E button. It just looks a little bit different. So don't feel left out if you have a Casio. You likely have that times 10 to the x button. So you would hit 6.022, and it'll look like times 10x 23. It kind of looks like that when you type it in. And you also do not need to use parentheses. You can just type it in just like that. All right, let's go ahead and try a practice problem. How many moles of sulfur are in 1.85 times 10 to the 24th atoms of sulfur? So remember that our conversion factor is 1 mole is equal to 6.022 times 10 to the 23rd particles. Remember, particles means either atoms or molecules. Go ahead, pause here, try this out, and then come back when you're ready to see the answer. Alrighty, so here we're going to start our train track with this entire bit. Okay, so that 1.85 times 10 to the 24th, remember, number, unit, chemical. So this is 1.85 times 10 to the 24th atoms of sulfur. So now we can make our train track. So we're going to use Avogadro's number to convert between atoms and moles. Okay, so remember this word particles here really is like atoms. Okay, so atoms has to cancel atoms, so that's why this half of it is going on the bottom. That means that 1 mole of sulfur will go on the top. Remember, number, unit, chemical. Number, unit, chemical. Okay, so now we double check atoms of sulfur cancels atoms of sulfur, and we're left with moles of sulfur, which is what we were trying to find. So when you plug this in, you'll get 3.07 moles of sulfur. Even if you are just watching along right now, please pause here and actually take the time to punch this in your calculator because I want to make sure that you're getting the right answer. Like I said, one of the things that people do wrong in this chapter is they're just punching it in their calculator wrong, and that would be an awful reason to lose points on quizzes and tests. If you are getting something like times 10 to the 46th or times 10 to the 47th, maybe even times 10 to the 48th, please know that you are very, 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 very wrong. And the reason that you're wrong is because you're typing it in your calculator. The answer will never, ever be to the 46th, to the 47th, to the 40 anything. I promise. That's never going to be an answer. Okay? If you're getting that answer, that means that you're just punching in the calculator wrong and you're not using the double E button or the times 10 to the X button, or you're not using them correctly. Okay? So here, what I would do is I would punch this in as 1.85 E24 times 1 divided by 6.022 E23. So again, the way that you get that double E button on the TI-30X2S is that you're going to use the second function, x to the minus 1, and that will put an E there. And then if you have the Casio, you need to find the times 10 to the X button, and it will put the times 10 to the X in place of these double E's. Okay, so just like I said, be really, really careful that you're not punching things in your calculator incorrectly. All right, so thus far we've converted moles to atoms and atoms to moles. But like I said, we can do this exact same thing with the number of molecules. Okay, so like here, this problem says 3.01 times 10 to the 24th molecules of carbon dioxide to moles of carbon dioxide. So we'll start with this, and the way we get from molecules to moles is by using Avogadro's number. So make our train track. So remember, this word particles can mean atoms or molecules, and in this case, we need it to mean molecules. So molecules has to cancel molecules, so we'll put that half down on the bottom, and we'll put 1 mole on the top. Multiply the top, divide the bottom, and we'll get our answer. So again, I want you to try plugging this in your calculator and make sure you're getting 5.00 as your answer and not times 10 to the 40 anything. Just be really careful with that. Alrighty, practice problem for you. How many molecules are present in 1.75 moles of carbon dioxide? Go ahead, pause here, and try this out, and then come back when you're ready to see the answer. Alrighty, so our conversion factor that we're going to use is Avogadro's number. 1 mole is equal to 6.022 times 10 to the 23rd particles. In this case, we're trying to find molecules, so we'll use it as molecules. All right, so our 1.75 moles of carbon dioxide goes in the beginning of our train track. And remember, moles has to cancel moles. So 1 mole will go on the bottom, and our number of molecules will go on the top. We'll make sure our units cancel, and we'll get our answer. Remember, even in your answer, you need to have number, unit, chemical. Okay? And also, you need to round for significant figures. Those never go away. For the entire rest of the semester, always round for significant figures. So here we have 3 versus 4, so we're getting 3 in our answer. Alrighty, so go ahead and pause here and complete problems number 1 through 8 on the Chapter 5 lecture worksheet. That will get you some practice using Avogadro's number. When you're done, come back and we'll keep going. So we were talking about before that we can't measure out individual atoms of carbon, right? I told you it'd be a bit ridiculous if you said, hey, hand me 4 atoms of carbon. Or even if you went to the grocery store and tried to just buy 4 grapes. People would look at you a little bit silly, right? In chemistry, we measure out our substances in grams typically, right? So we need to be able to relate the mole to the masses of our elements so that we can figure out, okay, if I know this amount of mass, then I know how many atoms I have, right? And remember, we use the mole to tell us kind of a bit about how many atoms we have. So that mass on the periodic table, the atomic mass of 1 mole of an element is defined as the amount of that substance that contains the same number of particles as exactly 12 grams of carbon-12, which I think is a bit confusing as a definition. So when it says 12 grams of carbon-12, the reason that we're using carbon is the periodic table is mostly based on carbon. A lot of things in chemistry are kind of use carbon as a definition. But essentially what this means is if I take 12 grams of pure carbon-12, so no other isotopes, just carbon-12. So 12 grams of carbon-12 is going to equal 1 mole of carbon, and that's going to be 6.022 times 10 to the 23rd atoms of carbon. So our atomic mass, or our molar mass, is defined as 1 mole of that element. Okay, we know already 1 mole of anything means that we have 6.022 times 10 to the 23rd of that thing, right? Like I told you, if you have a mole of puppies, you have 6.022 times 10 to the 23rd puppies, right? Because that word means a number, but they can vary greatly in the amount of mass. For example, let's say you have 12 quarters and you have 12 dimes. You have 12 of each thing, but if you were to put them on a balance, they would have a really different mass. Let's be even more drastic. Let's say you have 12 bricks. and 12 feathers. Well, you have the same number of things, right? But they have really different masses. The same is true for elements. You might have a mole of each thing, right? So you have the same number of particles, but they have really different masses because the individual atoms themselves have different masses. And we know those masses from the periodic table. So the molar mass on the periodic table is going to be the quantity in grams that equals the atomic mass of the element. Okay, so that mass on the periodic table, if you'll recall, was the mass of one atom of that element, but it's also going to be the mass of one mole of that element. And you might think, well, how's that possible? Okay, well, the mass of one atom of the element we measured in AMUs, atomic mass units. Those are very, very, very tiny units that are used to describe really small things. But that mass on the periodic table in grams will mean 1 mole of that substance. Okay, so if we measure out 6.022 times 10 to the 23rd atoms of that substance, it'll equal the mass on the periodic table in grams. Okay, so that's what we're seeing here. The molar mass is the mass of 1 mole of the element or the compound, which is the same as saying the mass of 6.022 times 10 to the 23rd atoms of that element, or the mass of 6.022 times 10 to the 23rd molecules in a compound. So again, if we look at the periodic table, remember the number on the top, that's the atomic number. That's telling us the number of protons. The number on the bottom, though, that is the molar mass. Well, thus far, we had called it the atomic mass, right, when we were talking about one atom, but we'll call it the molar mass when we talk about 1 mole of the substance, which is actually more common in chemistry for us to talk about 1 mole than 1 atom, because we really don't do much with individual atoms. So if we look at all of these have 1 mole of that substance. They all have 6.022 times 10 to the 23rd atoms of that substance. But if we went and weighed out all of them, you'll notice they have very different masses. Okay, because each of the individual atoms of that element have a different mass. So when we weigh that out, 1 mole of it will weigh different amounts. So the reason we need molar mass is because we're going to use it as a conversion factor. This will allow us to convert between moles and grams. And this is really important because in chemistry, we measure things out in grams. And then we do chemistry with it, right? Because again, we can't measure things out in moles. We can't measure things out in atoms. The only way we can measure it out in grams. So it allows us to convert between grams and moles and vice versa. So for example, 1 mole of magnesium is equal to 24.31 grams of magnesium. And I got this number from the periodic table. So if you find your periodic table right now, you'll see magnesium has a mass of 24.31. So that's an equality that I wrote here, right? 1 mole of magnesium equals 24.31 grams of magnesium. So therefore, I can use it as a conversion factor in my train tracks. So let's try this out. How many moles of lead does 15.0 grams of lead represent? So again, we're going to use this in the beginning of our train track, okay? In order to convert between grams and moles, we're going to need the molar mass. The molar mass is from the periodic table. So you're always going to need to have your periodic table handy. Okay, just in general, anytime you're doing chemistry, pretty much from here on out, you're going to need to use that periodic table because most of the time we need to know the masses of things. So if you look on the periodic table, you'll see the mass of lead is 207.2. Okay, that's equal to 1 mole of lead. So we're not writing down that equality, we're just going to know that the mass on the periodic table equals 1 mole. So we can use it, 1 mole on top and the mass on the bottom, or the mass on top and 1 mole on the bottom. It's just going to depend on how we need our units to cancel. Here, since we have 15 grams of lead, we need grams of lead on the bottom here. So the one that has grams of lead on the bottom is this one. So we'll put 207.2 grams of lead on the bottom and 1 mole of lead on the top. We make sure our units cancel, and then we've got our answer. You'll notice that I've rounded my answer to the correct number of significant figures, and in every box and my answer, I have the number, the unit, and the chemical. Make sure you do too. All right, I want you to try this out. This says, how many moles of mercury does 23.0 grams of mercury represent? To do this, you're going to need to find mercury on the periodic table and find the molar mass of mercury. Make sure your units cancel in your train tracks. All right, go ahead and pause here and come back when you're ready to see the answer. Alrighty, so we'll go ahead and we'll start our start our train tracks with 23.0 grams of mercury. Like I said, in order to convert between grams and moles, we're going to need to use the molar mass. So when you find mercury on the periodic table, you'll see that the mass of mercury is 200.59 grams. So we have 200.59 grams of mercury is equal to 1 mole of mercury. And we need to figure out, which part of that goes on the top or the bottom. Remember, grams of mercury has to cancel grams of mercury. So our mass of mercury will need to go on the bottom here. That means we're using this conversion factor. Okay, and 1 mole will go on the top. We'll make sure our units cancel, and we'll get our answer. All right, here's another one that I want you to try. What is the mass of 8.21 moles of potassium? Go ahead, try this out, and come back when you're ready to see the answer. Alrighty, so we're starting our train track with 8.21 moles of potassium. Since we're trying to convert between moles and grams, we're going to need to find the molar mass. So if you find the molar mass of potassium on the periodic table, you'll see that the mass is 39.10 grams. Moles of potassium has to cancel moles of potassium. So now we need our mole of potassium on the bottom here and the mass on the top. We'll make sure our units cancel, and then we'll get our answer. Okay, so the way that we write these conversion factors in the train track depends on what we're starting with, right? If we're starting with moles, then we need to have moles on the bottom so our units cancel. If we're starting with grams, like in the previous problem, then we'll need to have grams on the bottom so our units cancel. So just keep an eye on that. You don't need to write these conversion factors out if you want. You can also write out the equalities if that makes more sense to you, like this. Or you don't need to write those out at all, and you can just plug things into your train track if you can do it from there. This is whatever you need to write down to help you be successful, do that. But at the very least, you have to show work in order to get credit. In this class, remember, no work will get you absolutely no credit. So if you don't show any work, then I don't know where you're getting your answer from. So at the very least, you need to show how you set up the train track so I know how you got your answer. Alrighty, so that wraps up our first lecture of Chapter 5. Today we talked about the mole and how the mole allows us to count atoms without counting them, right? Atoms are so small that we can't see them with our naked eye, and we definitely can't go through and just count out a few atoms. So the mole allows us to determine how many atoms are in a substance without counting them. And so we learned that Avogadro's number, that 6.022 times 10 to the 23rd, that is what we will use to count our atoms, okay? But like I said later, that still doesn't really help us because in lab, we need to be able to measure things out in grams. So we needed a way to relate grams to moles and then moles to atoms to really know how many atoms are in our substance. So then we used the molar mass on the periodic table to say that that was the mass of 1 mole of any element. So now we are able to convert from grams to moles and moles to atoms, or the other way around, right? I want you to complete these problems, these 9 through 14 on the Chapter 5 lecture worksheet, to get some practice using grams and moles together, and you'll actually get a little bit more practice on using Avogadro's number as well. Make sure you get really good at these topics before watching the next lecture, because the next lecture will build on what we've learned today. So get lots and lots of practice. As always, if you're working through these, make sure to check your answers against that lecture worksheet key that's posted on Canvas. It's really important that you build good habits when doing these conversions, because these conversions are foundational for chemistry. Not just for this class, but even if you move on in chemistry, these are going to be really important skills. So it's important that you know how to do them and how to do them correctly. If you get stuck, feel free to send any and all questions my way. I am more than happy to help you out. Otherwise, keep working hard, and I will talk to you guys next time.